Hey, good morning, everyone. Thank you for joining this webinar. We'll give folks 3 minutes to join, so please bear with us here. It is 11:03 Eastern Time. I think we can probably go ahead and get started. We'll allow others to trickle in as we're ramping up here. A quick note to everyone, where everyone is able to unmute, but by default, everyone is muted. If you can, please make sure that you're on mute unless you want to ask a question or want to add anything. All right? Appreciate everyone's collaboration here. Okay, go ahead and share my screen. Okay, so we appreciate everyone joining here. We'll kick things off. Just to kick things off here, we'll go over the agenda from 11 a.m. to 11:10. We'll be covering the opening remarks and housekeeping items for this training session. After that, we'll shift to some PC preparation notes. Hopefully that doesn't take too long. So I think probably the first 2 items up there we'll probably cover in the first 10 minutes here. Then after that, we will shift to 3 hands-on training cases. The first one is going to be about BESS Project financial evaluation, how you can do that in a quick and simple manner within Storlytics. Second one will be more detailed. Definitely stay tuned for that one. So how to maximize project internal rate of return through market services driven BESS design optimization. And then lastly, the last hands-on training will be on a hybrid solar plus storage BESS project design. All right, so before we begin, just a brief overview about Storlytics. Storlytics is primarily a BESS design software. For those of you familiar with PV-Syst, it is very commonly described as the PV-Syst of BESSes. A couple of things make Storlytics stand out. Here we'll just go over 2 primarily. The first one is how much details are implemented in the battery models. The second is its capability to simulate and model not just lithium LFP, but long duration energy storage technologies as well. So when you add that to being able to simulate detailed project use cases, dispatching, and being able to input detailed meteorological conditions for BESS projects, you get the result here of Storlytics being validated to be the most accurate BESS design software out there by a third party. In this case, that was the Electric Power Research Institute. All right, so we have 2 main offices. Our headquarters is in Charlotte, North Carolina. We have a regional office in Cairo, supporting the Asia, Europe region. All right, and to shift to housekeeping here, please note that the entire workshop is recorded. By continuing to be here, you consent to the recording. Also, very importantly, this entire session is intended to be conversational. We encourage everyone to pose questions as needed. Our primary goal here is for folks to leave this session understanding and knowing how to design BESS projects. There's registered for this event is about 250 people, and we may see some more people coming in throughout the session. But so we appreciate everyone kind of raising their hand if they have any question, obviously using the Teams tool for raising hands. All right, for next one here, we'll be using Storlytics V4.1, which was recently released. We recommend people upgrade to this version, but if you're still on version 4.0, you should be fine throughout this webinar. If you need any Instructions, you should have received instructions from admin@storlytics.net about how to download, install, and activate your Storlytics license for free. If you haven't received this email, please check spam. If you have any issues, you can also send an email to admin@storlytics.net. Also, throughout the cases we'll be analyzing here, any pricing that we show is just for illustrative purposes. It does not tie to any specific company. All right, next here, our IT department prohibits the use of artificial intelligence note takers in online events or even just our regular internal meetings. So we appreciate everyone for not using their AI note takers during this session. Okay, introduction to the speakers here. I'm Sherif Abdelrazek, co-founding CEO of Storlytics. With me here is Jakir Hossain. He'll be covering the second case study we'll be going over. I'll be covering the first and the third one. All right, and let's get to it. Like I said, we'll be covering 3 main case studies. The first one is about project financial evaluation. Second, finding the optimal BESS design that maximizes project returns. And third, how to design a BESS project for a hybrid solar plus storage application. So for each one here, we'll be doing 3 main things. The first is the use case description. So in the beginning, we'll be spending some time explaining the exact case so that everyone's well oriented. Then we'll be developing the battery usage profile, which is how the battery system is going to be dispatched. That is very important for the simulation to determine degradation, losses, auxiliary load. All these factors depend on how a battery system is actually dispatched. So we'll spend some time on that for the cases. And then finally, BESS design for each case. All right. So case 1 here, BESS Project Cost Evaluation. Now, this is the part where we'll ask folks in attendance here to fire up Storlytics on their desktop if they have it installed, which we hope you do because we sent a lot of emails about that. But if you don't worry, you'll be able to follow along through the slides here. But if you do, it's a plus and you'll be able to follow along. All right, for the case description here, we're asked to provide an estimate for a BESS project that will be controlled by a utility as part of a tolling agreement with the following requirements. The required power capacity at the point of interconnect is 100 megawatts. The energy capacity, also dischargeable at the point of interconnect, is 400 megawatt hours, so 4-hour system. The cycling limit indicated from the utility is 1 cycle per day maximum, but of course, as you all know, in these type of tolling agreements that are common here in the US, they'll set a limit of 1 cycle per day, but that doesn't necessarily mean that they'll cycle it at exactly 1 cycle per day. Project lifetime for this case, 10 years. Location here, we're assuming New York, and deployment strategy, overbuild. And the requirement for the technology to be used on the project is lithium iron phosphate batteries. Now we can begin with the design process here. So here, bring up Storlytics. So this is what you should see when you bring up Storlytics. So here, we'll just give a name for this project. Let's call it BESS Financial Evaluation. And the first thing we'll start off with is the general tab here. So first thing we'll do, as the slides show here, is specify the project life, 10 years. And by the way, for everyone in attendance here, you should see the slides within the chat. Jakir, are we able to share that, please?
Yeah, I'm pulling that.
All right, appreciate that. So in case I go too fast or you need to go back to something, the slides are there or will be there shortly. All right, so for this case, we specify the project life as described in the case description. Then deployment strategy here will specify user defined. We won't be doing augmentation just for this example. Auxiliary load source here we'll do separate service. And to explain what this is, very commonly or somewhat commonly in BESS projects, auxiliary load will be sourced from a separate electrical service, not from the same point of interconnect. So in that case, you want to select a separate service for the auxiliary load source. But if your project doesn't have a separate service, then obviously your only option is to source auxiliary load from the same point of interconnect. And this project is transmission tied, so turn that on. Okay. And now we can move to the next step here, simulation options. So we'll turn on deduce financial results so that we can see the cost of the project and also revenue after we run the simulation. We'll also turn on the option to deduce battery degradation, which allows the simulation to calculate what the degradation will be each time step of the simulation based on how the battery system is being dispatched. For the initial state of health here, we won't make any changes. Its default is 100%, which assumes the battery cells are new. Some companies and users like to set this to 98% to account for some state of health loss during transportation or something like that, but really depends on your case here. But here we'll set it to 100%. And then finally here we'll turn on the option to deduce enclosure temperature regulation auxiliary load calculation. And what this does is it allows the simulation to calculate what the auxiliary load will be, which is primarily in lithium battery cases, HVAC load to cool the cells when needed or to heat the cells. And if your project is in a cold environment, you'll need to heat the cells. So this option allows the simulation to do that automatically. All right, now that we're done with the general tab, we can shift on over to the interval data tab. But before we do that, let's go back to the slides here and check the case. In the case description, the cycling assumption is 1 cycle per day for the tolling agreement. That's the maximum the utility set. To simulate that, we'll use the standard cycle here. And we'll specify that the target POI power is 100 megawatts. Duration is 4 hours, as the case implied. And then we'll put 1 cycle per day. Right? Now, then we can go to meteorological profile. So here, for those of you not familiar with TMY3, these are typical meteorological year files. That's what the TMY stands for. And it's basically a CSV file that has ambient temperature data, irradiance data, and other data about the location. These file formats are available for free online from NREL and other sources. So you're not limited to just the list that's already here, which is primarily for the US. You can also find these files for, like I said, online for free for really most countries in the world. All right, in our case, this project is located in New York, so we'll just find the TMY3 file for New York and select that. And then we'll shift on over to the equipment section here. So here, let's go back here. So for the equipment, we'll select a battery model, which is generic LFP 306 amp hour cell. Here, I'll go ahead and select that. And then SMA for the inverter, we're using an SMA Sunny Central Storage 3950 up. Some of you may be familiar with this inverter model. We've used it on multiple projects. Okay, and then finally for the enclosure, we'll use generic enclosure air LFP. Perfect. And for those of you not familiar with our enclosure models, the enclosure model basically controls how much auxiliary load is being consumed by the battery system. It makes a big difference if your enclosure is made out of steel or if it's made out of concrete or any other material. It also makes a big difference whether your enclosure is air cooled or liquid cooled. So if you open up the enclosure model, you'll find kind of all these specifications and the auxiliary load model here. You don't have to be super familiar with all these parameters to run a simulation. All right, so now we selected the models here, and you'll notice that the auto size project button came up. And just to take a step back here, so when you're trying to deduce what is going to be the cost of a battery system, your biggest unknown is the degradation that's going to happen to the cells, right? Because based on the amount of degradation that's going to happen, the cost of the system changes, because if you're going to get high degradation, you're going to need a bigger battery up front, or you're going to need more augmentations, and batteries are not cheap, they're expensive. Not knowing degradation really prevents you from being able to estimate what a project cost is going to be. All right, so that's why with the auto sizing tool here, once you specify the conditions here that under the general tab and specify how the system is dispatched and where it's located and the equipment you're using, then the system could be sized. Now, when you click auto size here, you'll see this window pop up. It'll show you basically a summary of the inputs you have. So we are designing for a 100 megawatt project, 400 megawatt hours. We're turning on degradation, obviously, because we want an accurate representation of the estimated cost of the project. So we have to account for degradation. Initial state of health, we're assuming 100% state of health in the beginning. And also, for those of you that may not be familiar with what state of health is the percentage of energy that the battery can withhold compared to that energy when it was new, basically. So if a state of health of 50% just means your battery can only hold 50% of the energy it could hold when it was new. Over build basis here, it's user defined, like we said. Over build years, 10 years, because the project life we're assuming here is 10 years, and we're not doing any augmentations. Okay, getting a question here. What factors are within the inverter selection? Cost, RTE. The inverter selection, of course, depends on the product. So if you open the inverter model here, you'll see for example, the efficiency table associated with this inverter. You can get this table from either the data sheet or the user manual of your inverter product. Auxiliary load, of course, changes from one product to the other. The capability, the apparent power capability of the inverter with respect to ambient temperature. The power capability, both discharge and charge with respect to the DC voltage. And finally, reactive power capability. So basically all these parameters are processed once a simulation is ran, and then the RTE of the entire system is calculated, which obviously includes the losses that are going to be within the inverter. All right, I think
We have one more question, Sherif.
Okay, when does the RTE factor come in? RTE is calculated within the simulation, so there is no RTE input to the simulation. It's calculated from every time step of the simulation, seeing how much losses are going in the battery, how much losses are going in the inverter, cables, transformers, and all other equipment within the project. All right, let's go back to auto size. So we went over these items here. We can then click OK. Then it'll tell us, all right, are you sure you want to kind of auto size with degradation? This may take a little bit of time. So here we'll click Yes. And what it's doing is it's running multiple simulations on the back end, trying out different project sizing, going from small energy capacity to larger. And every time it does that, it simulates the project and finds the degradation, and is trying to make sure that your target power and energy at the point of interconnect is always being met. All right. So while that is running, any reason we did not choose a liquid-cooled enclosure? No, there's no reason. It's just for an example. It really just depends on your project. Most people like to go with liquid-cooled enclosures because it's just more efficient, about 60% less energy, or rather 40% less energy consumption than air-cooled systems. However, the only downside of liquid-cooled systems is the extra maintenance that is required for them compared to just air-cooled, which is just primarily like in your home, changing your air filter on your HVAC. What are the most popular types of enclosures used? I'd say, since right now there's just a lot of kind of pod enclosures that are pre-manufactured by the integrator, folks like Fluence, not FlexGen, but Powin and Sungrow and others. And primarily it's steel enclosures with liquid cooled, I think, is what's most common. All right, so auto sizing has completed here, and you'll notice that all the parameters in the other tabs have been filled out. Under system specs here, the number of modules per rack has automatically been set to 8 modules per rack. So here, these have been set to 8. The number of racks per inverter to 42, and number of inverters for the project has been set to 30. You'll also see that the losses have been specified. For transformer copper losses, the default assumption is 1%. For core losses, 0.1%. And here we're assuming 0 auxiliary load losses. And when I say auxiliary load losses, this is the constant component of the auxiliary load losses, which does not include the HVAC. So here, if you read the hover message here, it's control devices and excludes enclosure and HVAC load. Operation, maximum state of charge has been automatically set to 95%, minimum state of charge to 5%, and the initial state of charge for this simulation is 10%. Okay, now we can shift on over to the financial tab, which is the main reason why the run button is not enabled here, because the contract term for the tolling agreement here is needed to be input. So we know the project life is 10 years, so we can just put 10 here. We'll see that the run button here has come on. Right. I have a question here. Is there a differentiation in nominal, netto, brutto values?
John, can you unmute yourself and maybe elaborate on that point?
We can
Yes.
just,
Hi, hello.
yes, go ahead, John.
So the question is whether you differentiate between the losses. If you input the values, sometimes we put net value or the gross value, which is after internal losses or conversion from AC to DC.
Okay. Yeah, I think it'll become clear how losses are calculated once the report is produced here. And to be clear, we're not inputting any kind of percentage losses. The losses are automatically calculated within each component. So here, since the simulation is done here, we can generate the report. And then first thing I'll do is I'll go to that loss section to address your question.
Thank you.
So here, let's just go to the Sankey diagram, right? So here, this is basically a summary of all the losses in the system throughout the simulation. About 146 megawatt hours were charged at the point of interconnect. 1.16% of that was lost within the generation step-up transformer. And then you can see these percentages here, 0 for the secondary GSU system. So on the other side of the GSU, basically, that's 0. And then within the PCS, you have 1.24% losses. Inverter charge here, 1.58% losses within the inverter. Within the battery, you can see that within the internal resistance, the series resistance here, 1.61%, 0.02% self-discharge, because here we have a lithium model, and lithium has somewhat low, very low self-discharge if you compare it to nickel hydrogen or zinc batteries. Finally, open circuit voltage hysteresis data. And then, so this is all while the system was charging, and you have the same values while the system was also discharging. Okay, and back to this point here, the reason these are all zeros is because if we go back to our simulation here, auxiliary load is being fed from a separate source, not from the point of interconnect. That's why there's no kind of, it's all zeros here. If we had it as auxiliary load to be fed from the point of interconnect, you would see the values here. All right.
Sherif, there is one more question along this line. So what about the grid code conditions such as power factor? Can I input this in the software to take it into account for sizing PCS?
Yeah, very good question. Yes, you can input a power factor, and power factor is already calculated. So the default power factor in the standard cycle is 1 at the point of interconnect. But if you wanted to set, or rather for market signals is 1. If you wanted to set a lower power factor, because some jurisdictions require 0.95, 0.93 capacitive power factor at the point of interconnect, you can set that. And also, if you're just using a time series here, you can, within here, we go to the user files, input profiles, POI profiles. So all these CSVs, these are the ones that show up in this list, okay? If you open up any of these, let's just do this one, you can see that there's basically 3 columns. One is the sample time, the second is the power, the third is the power factor. So you can have a different power factor for every time step, right? Okay, so let's come back here, standard cycle, and simulation again. And we were going over the report. All right, so now when I clicked generate report, this report came up. Of course, we just went over the losses section, but since this case study is about the financial results, I'll just fast forward to that section. And then if there's any questions, we can go back to any of these sections here. All right. This is the financial section. Everything is laid out in a table format to begin with. I won't go over line by line here, but I'll just jump on over to the figure. So here you have a net present value chart. So it's telling you what's the overall cost of the DC block in this case, based on how much degradation was calculated and the resulting beginning of life capacity. So if we go to this chart here, you can see that the beginning of life capacity we have is about 557 megawatt hours were needed for the project to be able to last for 10 years and maintain that energy, that 400 megawatt hour target energy capacity at the point of interconnect. And that ended up costing a little over for the DC block. Let's see here. right? About $90 million. Then you can see the PCS cost portion, GSU, high voltage breaker, and then depending on how kind of detailed you were with your financial model and what kind of cost components you want to include. So here I'll just include all these and run another one. But the more kind of parameters you add in here, the more detailed the financial results are going to be here. I think I should have actually had them on in the first one here, in the first simulation. All right, so while that kind of is running, you can look if there's any questions.
Yeah, I don't think we have anything pending.
Okay.
Only thing is Pedro wanted to learn more about the revenue model, so we said we're going to cover it in detail in the second example.
Okay, perfect. All right, so I can probably pull up another report here. There we go. All right, so here, all right, for annual OPEX breakdown, you'll see the energy loss cost over the project lifetime here in light blue, and then the state of health guarantee cost in dark blue. Of course, the state of health guarantee is not there for the first 3 years because the standard warranty assumption on the battery is 3 years, but all of these parameters you can edit within the financial model, which is this one. The good thing about this is since it has a model format, you just need to edit it once based on your case and save it, and then you can use that with all your kind of project simulations. So under cost here, you have the equipment cost section, which includes the battery, the PCS, the GSU, and high voltage breakers. OPEX costs, so standard warranty, so we have that as 3. That's why you didn't see any state of health guarantee costs for the first 3 years. State of health cost at year 0. State of health cost change rate, if any. Auxiliary load, energy cost, losses. And even though it's not relevant for this simulation, but for augmentation cycles, if there are any fixed amounts per phase for each augmentation, which there obviously is, so you want to have that filled out. Augmentation phase change rate, auxiliary or augmentation energy dependent cost, and also here balance of plant. And Jakir will get into the details of these parameters in the next case study here. All right, so here, then we can go to the revenue side of the equation. So since this is a tolling agreement, you can see fixed revenue over 10 years. Of course, if we had it set as a merchant market, you'd be seeing variable kind of revenue depending on what the battery is doing based on the simulation. But here it's a tolling agreement, so it's a fixed revenue. Also, we didn't assume any liquidated damages for RTE, for availability, just for the sake of simplicity here, but we can turn these on in a real project kind of evaluation. You would definitely want to have these parameters on to account for any LDs you may be paying based on underperformance. And then here, the overall cash flow, so how much you're spending in the beginning of life of the project, and also the revenue throughout here. Now, because this is a overbuild, so the IRR doesn't look as attractive as probably you would get on a lot of projects when you augment, but this is just obviously for the purpose of demonstration. Right, and then here, discounted cumulative cash flow showing break even at year 10, so not so good. Obviously, this is an overbuild project. All right, coming back here, let's go to the sides here. And the slides here are very detailed, and we obviously sent them through the chat. So for those of you who may have missed anything, you can go back to them. Right. So we covered the degradation, the costs here, the revenue, right? Now, observations here. So we were able to deduce the preliminary financial estimate for this project right now within 44 minutes, not 30 minutes as the slides say. We've been able to do that in less than 30 minutes previously, but all right, second one here. Something you may have noticed is we did not need to input any assumption on degradation rate. We just described how the system is being dispatched, selected the models that are planned to be used in the project, and degradation was automatically calculated because, like I said, it does make a huge difference how much degradation per year is happening as it relates to the beginning of life capacity of the system you'll need, which heavily affects your capital cost and also augmentation costs. Right, inverter capacity was automatically oversized to meet reactive power requirements. So our project actually needed just 100 megawatts at the point of interconnect. You'll see here that our total inverter capacity is 118 megawatts or MVA. And this is mainly to account for the reactive power that's being consumed within the transformers here between the inverter and the point of interconnect. Obviously, if we increased or decreased the power factor requirement at the point of interconnect, in other words, if more reactive power was needed at the point of interconnect and we're not at unity power factor anymore, you would see this number go up when we auto size. So after we do the auto sizing, you'd find that you'd need more inverter capacity to just inject reactive power into the grid. But you don't have to guess about that. Once you just click that auto size button, it'll automatically be deduced based on kind of the simulation. All right, then finally here, since I alluded to this one, since we're overbuilding for 10 years, Project IRR is not that attractive. So more than 50, you can notice that more than 50% of project net present value is for the DC block. So that's why. Right, so now what? If this were a real project, the next thing you would do here in this case is you obviously want to improve your project economics. You don't want to break even after 10 years. You want to break even probably about a very good project would be like 3 years, 4 years or so. So you try different technologies. Something that will be very effective is running the augmentation optimizer to optimize when you actually do an augmentation. And that kind of, we've seen in some cases, will reduce kind of net present value cost at about 15% in some cases. So very impactful and does not affect the performance of the project in terms of kind of the functions it is performing. Second thing here, optimizing battery selection. So we can now go back here and see, all right, we tried it using, in this case, we did a generic battery, but if this were a real project, you'd want to use any of these OEM models. And then if you're finding that it's not performing well, you can try others until you get performance that is heavily suits your project requirements or is more kind of financially advantageous. And finally here, so if everything looks good and we're satisfied with the system design, then we can generate a one-line diagram for the system that's been designed in preparation for any IR applications or any kind of next steps for the development of the project. All right, so that's everything I have for this one. We can probably open that up for questions.
Yeah, actually, we have a question in the chat from Pedro. Can you explain the 557.4 megawatt hour? Does this ensure a minimum usable energy capacity of 400 megawatt hour for the 10 years?
Yep, yeah, very good question. Yes, it absolutely does. That's the whole point of overbuilding and auto-sizing. And I'll go over the section here. So this chart here is for the energy dischargeable at the point of interconnect. So you can see here at year 10, you still have a little bit of buffer in the energy that is dischargeable at the point of interconnect. Now, to get this, right, let's see how the energy capacity at the battery terminals looks like. So the energy at the battery terminals at year 10 is 494 megawatt hours. So some of you may say, that's a lot. Why do you have, since you only need 400 megawatt hours at the point of interconnect, why do you have 494 megawatt hours at the battery terminals? It's because there's some factors that you need to account for. So for one, the operation range. So there is no battery out there that you can cycle from 0 to 100%. And when I say from 0 to 100%, I'm talking about the actual installed energy capacity of the battery, not the commercial kind of rating that some integrators and OEMs will use. So some OEMs and integrators will say, yes, you can go from 0 to 100%, but most of the times they'll be referring to a commercial kind of rating of their battery system, which is less than the actual installed energy capacity. So here, everything that Storlytics uses is actual installed energy capacity because it's almost a physical, it's not really a physical model, but there's no commercial kind of calculations within we're not accounting for any kind of commercial nameplates in here, right? Because the primary focus here is accuracy. This is basically 10% here, so that's 40 megawatt hours. And then the rest is, if we go back to the Sankey diagram here, so you can see when you're discharging, you're losing energy within kind of the battery itself. You're losing energy within your inverter, you're losing energy within your medium voltage transformer, and you're also losing energy within your GSU, right? So all of that is taken into account in the sizing. Hopefully that answers your question, Pedro.
Yes, very clear. Thank you.
Yep, sure thing. All right, see a question from Muhammad Shahab. What is the investment tax credit we assumed in this simulation? So let's see here. Let's open up that model. So here we did not assume any ITC. That's a contributing factor to the ugly kind of financial results, or I shouldn't say ugly, the not so favorable financial results. Let's see, any other questions here? All right. So I think if there are no other questions, we can shift to the next case here. So Jakir, you want to kick that off?
Sure, let me grab the screen real quick. All right, share my screen here. Okay. So now we're going to shift gears. So the first use case give you a very good understanding about the flow of the design, how you typically go about doing it, and how quickly you can really simulate and get to the financial and technical results. Now, this case is going to be more about optimization. So when you are trying to develop a project in a market, there are a lot of different variables associated with that and a lot of decision making that needs to happen. So you have market dynamics, the signals, the way the batteries are going to be dispatched in the market is going to vary from market to market and market rules. Obviously, the location is going to have an impact on your auxiliary consumptions. And then if you are trying to optimize your return on the project, you are looking for favorable or optimized augmentation strategies. So you probably want to build less upfront and then trying to come back and add capacity at different years so that you can maximize your return. So all these questions, if you are trying to make more firm decision, that needs to be informed by more detailed and accurate simulation. So this case study here, we're going to try to run through some of these design parameters that can impact your basically decision making. So the example we have on hand is a similar 100 megawatt for our project, but now it's going to be market specific. Previous one, it was just one cycle a day. Now we're going to be focusing on an ERCOT North market. So we'll see how can we generate a market signal and then utilize that to do our design. 20 years, deployment strategy is going to be augmentation. So that's different than the last case. It was a 10-year overbuild. Now we'll try to come up with an optimized augmentation strategy. Obviously, location ERCOT North, the battery and inverter will keep the same. And if we jump to the software interface, let's start a new file and give it a name. We'll go ahead and then save this file. All right. So once we have saved it, we'll come here under General. We are going to define the power and energy requirement. So 100 megawatt, 400 megawatt hour, 20-year project life. Under deployment strategy, we will select now augmentation. And you will see as soon as we select augmentation, these two tabs here, augmentation and financial, both become enabled. Because augmentation, when we are going to do that, and we will use our augmentation optimizer feature, that is also going to use the financial parameters. And I'm going to cover that more detail. So you select that, then you come to the auxiliary load source. You can choose whether to do it from separate source or POI. Previous example was a separate source. This example, we're going to do with POI. And that basically means that your battery is going to be supplying the auxiliaries. So obviously that's going to result into some more throughput coming from the battery. And you'll see the impact of that on the degradation as well. Eventually, you select the transmission type project. So that brings us the GSU. So select T-type under interconnection. And then under simulation option, we're going to select all the three options that are available there. First option, financial results. We will look at that because we want to optimize the project return. Reduce battery degradation. Big part of it is based on how the battery is going to degrade. So we're going to enable that. And the last one is the reduced enclosure temperature regulated aux load. A big portion of the auxiliary consumption for battery sites really is being consumed by the heating and cooling. And that depends heavily on the ambient temperature, the C rate, and the enclosure design. So when you enable this option, that allows you to get that variable temperature auxiliary consumption that varies with these parameters. Once you have done that, you go ahead to the interval data. And previous example, we used standard cycle. This example, we're going to use the time series. When you select the time series option, what the program is expecting it to input is a charging discharging pattern in terms of power profile. And this is where we can use the generate from market signal feature that we have in the platform. So if you click here, we are targeting ERCOT market. So you can come here, you can input the power capacity, you want to commit to the market. So in this case, we're going to commit the full capacity, which is 100 megawatt. And the duration is, there are 1 to 6 hour duration that you can choose from. So we are focusing on 4 hour for now, this example. You select 4 hour. And then if you can select this drop down, if you select the drop down, you will see that all the 4 hour market signal that are available. So right now the platform support all 78 areas in North America, so New England. So all the major markets are here, and that includes market in Canada as well. So in this case, you can go ahead and select ERCOT North signals, this one, because that's the market we're targeting. Once you select that, then you also have the option which year you're going to take as your design basis, because we provide up until 10 years in future the forecast of the market. So you can choose whether you're going to use 2026 for your basis, or if your project placed in service is 2029, let's say, you can choose that as well. So I think, for example, this one we just did 2026. Once that is done, you will go ahead and give the file a name. And then you'll go ahead and click Generate POI Profile. So what it does is, you might have noticed that as soon as you click this, it populated this field here. See that in the CSV file? That ERCOT not 2026, that's the CSV file we just created. So it basically generates that CSV file and it populates it here. And then if you go under diagrams on the right-hand side here and go under POI profile, under POI diagrams, you will be able to see how that profile looks like for it. Okay. And then this is a power profile. So negative basically means charging, positive means discharging. Now, some of the folks might have questioned. I mentioned North American market. So if you are in a different market like UK or Europe, how are you gonna input your own signal? So one of the thing to note here is this feature, yes, it does support North American market now, but you can also bring in your own signal. So if you are in a UK market, you can get the historical data for that market and you can import it through this option because this is a CSV file format. So any data that you have, if you organize that into the CSV file format and add it into Storlytics user files folder, you will be able to select that and use that as your design basis. Then we move to the TMI data option. One of the critical information input is that a lot of the performance depends on the location of the project and ambient condition. So the way you tell that to the program is through the TMI3 profile. So this is a typical meteorological data profile. So it has ambient temperature condition. So we're going to go ahead and select Texas. And typically, even if you are outside the US or North America, if you go to the NREL NSDRB website, you will be able to give your location and download the TMI3 file for your location for free. And you can download the file and you can add it into the Storlytics user folder, and you will be able to select it if you are in other parts of the world. So we did interval data. So once that's done, you move to the equipment. So under equipment, you have two options, two ways you can input your equipment information. You have standalone models or integrated models. So for standalone model, you have to tell which battery models, which inverter model, and which enclosure model you're planning to use for this simulation. And if you select the integrated model, so in that scenario, it's more of a integrated product that you will be selecting. So you can go ahead and select a Sungrow or a Tesla or other integrated products. If you select that, for example, in that case, you will see that based on that model, the standalone, the battery and inverter enclosure is going to be automatically populated. For this example, I'm just going to use the standalone model option. So we're going to use standalone for the battery so that everybody can run it. We are going to use a generic model. So you see this one, so generic LFP 280 ampere hour. Inverter models, we will use the SMA SCS 3950. And then enclosure also, we're going to use the generic model so that everybody can follow along. So once you have selected the equipment, so you have done the general interval equipment, next important thing that you have to input is your financial model. So you will jump to the financial model parameter. You will come here, and this is where you have to input the financial model that you want to be used by your augmentation. If you click this green button here, that gives you access to the financial model editor. So in that way, you can go in there, review the parameters, and basically update them and save it as your own file. I'll go ahead and walk you through some of the parameters that are in here. So the financial model initially starts with, there are some generic parameters around your financial model. So you will have your discount rate, and that's important because a lot of the calculation the augmentation optimizer does, it looks at the net present value of your overall cost of ownership. So everything is normalized with respect to present value. So you input your assumption on discount rate there. If your project is eligible for ITC, you can input it here, your ITC percentage. You can also define at what year you want your ITC to be applied, because a lot of times your ITC doesn't get applied immediately at year one. Depends on when you basically file it. So you can do it at year 2 and 3 as well. You also can choose what percentage of your CapEx is ITC eligible. So if there are certain portion that is not eligible for ITC, you can control that through this parameter. You can also select your depreciation. So you can select your Makers 5 method, or you can do bonus 100. If you do Makers 5, you have the default schedule, but if you want to give any custom schedule based on your country or location where you are at, you can go ahead and update the CSV file, and that will allow you to input your own depreciation schedule. You can also input your corporate tax rate, because that allows you to calculate your savings because of the depreciation. And also you can control, typically there is a 50% reduction factor. If your project is ITC eligible, your depreciation basis is reduced by 50%, at least here in the US. So you can control this parameter based on your project specs. Once you have done setting up all this, then you can go ahead to the cost parameter. So the cost is divided into 4 main categories. Sherif covered it quite a bit, but I'll just go over them briefly. On the equipment cost, you basically input your battery dollar per kWh, any future rate that you are predicting the battery price is going to go down. And especially for augmentation, this is an important parameter, because that declining cost of batteries are going to have an impact when the augmentation optimizer is going to tell you to add batteries. So if you have 3% versus 5% versus 1%, you will see that augmentation schedule is going to vary based on that. Similar to your power electronics cost, as well as your change rate, you also your GSU cost in dollar per kW, and also high voltage breaker cost you can input. Then you go to their OPEX, because we look at the overall total cost of ownership. So you also have to input some of the OPEX information. So standard warranties, SOH guarantees in dollar per kWh basis. A lot of times there is going to be escalation in your maintenance contract. So you can input those escalation percentages. Also, there is going to be the rate for your auxiliary energy losses. Obviously, these systems are not 100% efficient. So you will need to pay for those energy losses. So you can set the rate for your energy loss, and also
Jakir, so this parameter was asking about this parameter, if they can edit that. So how much for your benefit, this is where you can edit the rate of applied, or the tariff applied for energy losses, not just the rate itself, but also the rate of change of that rate in the next parameter. You can assume that, okay, every year for maybe energy is getting more expensive. So in this case, we're assuming 2% increase in yearly cost of energy here.
Yeah, thanks a lot. That addresses my point. Thank you.
Sure.
And what I meant for the financial model, I meant when you save, this will be my file that shows later on, or among the, it's not an external file to choose from. It's something I built and save.
Correct. You can save it, and it's local to your computer. It's not on the cloud, or nothing in Storlytics is on the cloud. So everything's local to you.
Okay, great. Thanks a lot.
Yeah. So you have your auxiliaries, and then you have a separate loss for your, basically your system losses, transformers, balance of plant, and others. Typically, if you set it to be fed from POI, it's going to apply same rate for system loss and auxiliaries both. But if your auxiliary is being fed from a separate source, and you have a different rate for your auxiliaries and a different rate for your system losses, you can actually divide them up and set different rates for them. So that option is also available. Then you go to the augmentation cost. Of course, when you are doing augmentation, there are some costs associated with that. There are some fixed costs like plant integration, project management, and controls integration and others. So you can input them, and you can also input that because labor is getting more expensive with time, you can also input the percentage that those are going to be escalating. And then there is also some part which are basically it depends on how much capacity you're adding, right? So maybe adding 5 inverter versus 10 inverter and 5 battery block versus 10 battery blocks. So you have to do foundations, civil works, and others. So those are your capacity dependent parameter that you can update, and that's taken into account in the backend. And last but not the least, we have the balance of plant. So this is where a big portion of your overall project finance is also the EPC cost. So this is where you can input your interconnection cost, fixed cost, variable cost, your EPC engineering cost for electrical, civil, actual electrical work and civil work, project management, commissioning, any kind of fees. Pretty much all the details typically you need can be added here, as well as owner's cost. So that covers us on the cost side of the equation, and then we jump to the revenue side. So on the revenue side, since we are in the topic, for augmentation optimizer, we mostly focus on the cost because augmentation optimizer is trying to get you to meet your technical requirements at the least cost possible. So cost is the most important for the augmentation optimizer that we will be running. But the revenue is also important when we are going to calculate the IRR parameters. So I'm just going to walk you through the revenue options that you have. So we have two different.
Real quick, got a question from Pedro. Does the model optimize the augmentation plan based on input augmentation costs?
Correct. It takes the input augmentation cost. It looks at the equipment that you have selected, and it also takes at the use case that you are using. So it combines all these 3 factors, and based on that, it determines the optimal augmentation schedule. Okay. Hope that addressed that. If there's any follow-up, let me know. All right, so we are talking about the revenue. So revenue, we have 2 structures, tolling agreement and merchant market. So tolling basically is your typical PPA structure. If you are doing a fixed capacity tolling, you can set that in $ per kW month. Typically with your tolling agreement, there is going to be some performance matrices associated with that. And those are typically, you have to maintain a capacity, you have to meet a certain RTE, and you typically have to be available at a certain amount of time. Otherwise, there is going to be some LDs associated with that. So you can set those LD parameters as well. So in that way, you can determine if your project is underperforming, how much hit you're going to take on the revenue side. And then there is also merchant market option. So in the market option, you basically make money depending on how the market rates are and how we are dispatching the battery in the market. So I think Mohammad Shihab also had a question about, can you do merchant market ancillary as well as capacity together? So yes, you can. So the way it works in the first part, market services, this is a CSV file. So you see that it is inputting the pricing from your market. So you can actually input that into CSV format from your market. And if you expect that those rates is going to be changing year over year, you can input that here as well to the rate adjustment factor. So that's based on market merchant services. Now, if you want to stack a capacity service, maybe like a PJM, you can do that to the capacity payment. So you can come here, you can select some of the parameters like ELCC, penalty factors for capacity payment, what is the clearing price for the capacity market in $ per megawatt day, if those are going to be changing. And typically these contracts will also have an annual penalty cap. So you can set that as a factor as well. All right, so I think I covered the financial model in detail. So practically taking us back to our original question is we want to design the project and get the augmentation schedule. So once we have inputted the cost, we're going to go back to the augmentation tab and we will utilize the augmentation optimizer option. So there are 2 options here. You can bring in your own augmentation schedule if you have one, and the program will help you to show you the results based on your augmentation schedule. And then this augmentation optimizer option is where Storlytics optimize the the augmentation schedule for you and define it for you. If you select that option, you go under augmentation optimizer. You have to select whether you want to do an AC augmentation or DC augmentation. It also depends on the type of product you have selected. Based on that, you can select AC or DC. And then there are 3 parameters that you can choose whether you want to define to make the optimization search more restrictive, or you want to make it more broader and let the program choose it. So for each of the parameters, you will see that there is a user-defined option and a Storlytics optimized option. So if you select Storlytics optimized option, then you don't have to input anything. The program is going to run thousands of scenarios in the backend and then going to give you an optimal schedule. But a lot of times, teams might have preference that I do want my initial overbuild to be 3 years. I'm not going to take anything less than that. So in those scenarios, you can actually come and define that parameter yourself. All right. So once you selected these inputs, you then can go ahead and click the Run Augmentation Optimizer, and in a message box will pop up telling you that this will need some time because it's running a lot of scenarios in the backend. And if you click yes, the Augmentation Optimizer will start running. Now, depending on your machine speed and the amount of options that you have given here, it might take some time. But after you have done running, it is basically going to generate an augmentation schedule and populate that here in the second field called the augmentation schedule. So you will see after successfully running the augmentation optimizer, an augmentation schedule is being populated here. So I'll skip running it now for us to save time. I have already pre-ran it. So if you go to under File and Open and go to Open, you should see there is a project file name example ERCOT BESS_AC. Click on that one. Yeah. So that one I ran pre-built, and when we ran the augmentation optimizer, it generated an augmentation schedule and populated it. Now, what do you expect to see when the augmentation optimizer successfully runs? So let me show you some of the results that you are going to get. Going back to the slide. Okay. So when the augmentation optimizer runs successfully, you will see that there is a show results button under augmentation optimizer. It is going to become enabled. So this button here is going to become enabled, and you will be able to click it, and that is going to give you access to these images. So there are basically 3 output images from the augmentation optimizer. The first one will show you that all the scenarios that it has run. So in this particular case, it ran 59 different scenarios. And the one that it found to be most cost effective was the 7th one. And that is about 7% less expensive than the most expensive option that it evaluated. So you are actually getting 7% in saving by optimizing your augmentation strategy in this case. Then it also is going to give you that POI capacity, right? Because one of the goals here is you want to make sure that you get an augmentation schedule that maintains the capacity throughout the project life. So here it will show you that it is telling you that you are able to maintain 400 megawatt hour throughout the 20-year project life. And it is recommending in this case, year 3, you come back and add some capacity. Year 7, you come back and add some, again, more capacity. And then year 12, you add some additional capacity, right? And then the other image, the second image, it will show you here is the degradation estimates for all these different phases. And you will notice something in these graphs is the blue one here is your initial build. That's the initial system that you put in. And then you have phase 1. That's the new system, augmented system that you added. The green one is the second augmented, and the red one is the third augmented. And the degradation, if you pay attention, you will see that the degradation curves are not the same. They vary because when you add more capacity, you actually are not stressing your initial system as much. So you're putting in less stress to that system. So the degradation rate of your initial system is going to slow down. So that kind of dynamics are captured through the augmentation optimizer. So we do not apply the same state of health estimation for all the different phases. It's derived based on the system capacity and the signal that is going to be executed. Is there a question?
Yeah, Mohammed Shahab has his hand up. Go ahead, Mohammed. Mohammed, if you're talking, we can't hear you.
Sorry, I wasn't muted. It's related to the multiple revenue streams. Maybe we can do it after Jakir is done, or when we have time to go back. And I'm not sure if I understood it.
Sure, we can do it. No, that's fine.
So my understanding is that you can do merchant plus capacity, correct?
Correct. Yep.
It's only two. So if you want to add frequency response, let's say, to these two, I have to do a separate simulation for that.
Yeah, so if you are talking about frequency response, we have to look at the typical revenue stream. So the way we typically do it, any kind of ancillary services revenue is going to be inputted through this revenue file. So if you have multiple revenue happening in ancillaries and other services, you'll input that through the market service rate file.
So my file has to incorporate the multiple services I need to simulate and under that market service section here.
Yeah.
Okay. Okay, that's explained. Thanks a lot.
All right, so let's go back to our discussion. Okay, so that's how the augmentation optimizer works. After you are successfully running it, it is going to populate this augmentation schedule, and then you are all set to go ahead and click the run button. But before we click the run button, I also want to review some of the revenue option that is here under financial. So we covered the model in details. On a project level, you also need to make some decisions. So here under revenue, you can choose whether you want it to be a tolling agreement or a merchant market, right? So if it's a tolling agreement, you select which is your placed in service area, year, what is your contract term, you can input that. And then you can enable or disable some of the performance matrices depending upon what you have in your contract. So you can enable energy capacity LD, enable RTE LD. So you have to set your guaranteed RTE. So if you, after the simulation, if your project is underperforming, you will see the impact of that on revenue. And then also the availability. You have to set your availability target and what your assumed actual availability. Once you've done that, you basically can then go ahead and run it.
Hey, Jakir, there's a question about I think Sana is asking about the augmentation optimizer feature, if it's available in the trial. We probably should have mentioned that. The augmentation optimizer feature is only available in the plus tier of Storlytics. No, it's not there in the trial. That's why you're probably going to see it grayed out.
Yeah, good reminder. Yeah, sorry, I forgot to mention that. But yeah, you should be able to run this pre-built example that we provided. That one should still run in the trial version. Okay, so while it runs, it might take a few seconds to run. I'm just going to go ahead, let it run, and go ahead, jump to the report. People who are following along, once it's finished running, you can click, the generate report is going to become enabled, and you can click that. And let's go ahead and review the report here together. So once you finish running and generate the report, you're going to get a report like that. A big portion of the report was already covered in the first segment. I want to touch base on the one that we didn't cover in detail. So first, a big portion of the report here will help you to assess the design that you have done. So in this case, what in the screen is showing you that in blue that what was actually required in terms of power by your system. So the profile that you have inputted, right? Because remember, our design basis here is this profile that we have given. So the blue here is showing you at different locations on your system, what is the power requirement. And the green here is telling you that what you are able to achieve with the system that you have designed. So here we see we're completely meeting it. So we're good from a power sizing perspective. On the energy side, we can see that we are falling short a little bit on the discharge side. We're not 100%, we are around 97 to 98%. Now the question obviously becomes, why is that? So the radar chart gives you the summary, telling you that yes, you are falling short a little bit on the discharge side. And the donut chart here is exactly telling you why you are falling short, where it is telling we are falling short about 1.76% of the time because of hitting the minimum SOC limit. That means the signal that we are giving and the system that we have designed, that signal is not charging this system enough, or the system is having more losses than that signal assumed. So we are all draining our battery more and is not able to follow that signal fully. Then the next part is important for your efficiency. So here it's telling you that your 1 cycle per day efficiency is going to be around 85.48 round trip efficiency. And if you remember, the guaranteed efficiency we gave is around 88%. So for this case, my system is underperforming. So we'll see that what is going to be the impact of that on our revenue. Then it also gives you the breakdown of your auxiliaries. And that's the point I made very earlier, that auxiliary consumptions depends very much on your ambient temperature profile. So here you'll see in Texas, in summer, it's consuming a lot of auxiliaries because it's having to do a lot of cooling, but in other months, it's not having to do as much. So here it's a monthly breakdown of your auxiliaries. There are different components of your auxiliaries. So all these are broken down in very detail. And in the Excel raw data that you can also generate from the simulation will give you every time step auxiliary consumption. Then you go about looking into some of the characteristics that how you actually utilize the battery. So here it's telling you that obviously you can see throughput and cycles per day. This use case was the battery was used heavily in the winter, sometimes more than a cycle, and then summer as well. But on the shoulder months, it was not being utilized as much for the use case that we ran. So the usage is varying. It's not a constant 1 cycle per day. It's varying depending on the market scenario. And then it gives you this state of health estimation that is completely based on the location, based on the use case profile of your project. So it tells you state of health, capacity, DC-DC, RT, POI, everything is specific to your project, not based on generic assumptions. Then the most important check is this, right? Because our eventual goal is we want to get the most cost-effective solution, but it needs to meet our technical requirements. So here you'll see that in terms of capacity, we can see that the augmentation schedules that we got after executing them, the project is going to be able to meet 400 megawatt hour throughout the project life, and it's very optimally done here. Then the big portion of the discussion is around net present value of cost. In the first example, we covered it, so I'm going to skip that. On the OpEx side, I want to highlight a couple of things here. So you will see that there are some certain jumps happening. Those are the year basically we had to do and come back and do augmentation. So augmentation is part of the OpEx cost. And you can also see the different breakdown of your augmentation cost. The green one is your battery cost. This was an AC augmentation. So you had inverter cost as well. And the gray one is your augmentation, basically ancillary cost for your augmentation, site works. Now on the revenue, this example, we did a fixed tolling agreement, right? So the revenue, that's why you see it constant, not changing, fixed constant on the revenue side. But what you'll notice here is that on the negative axis, there are some penalties happening. So we will see that RTE, that I mentioned that we are falling short, you will see that RTE LDs is basically increasing with time, because with time, at year 0, our RTE is less than the 88%. And then with time, RTE is going even down, right? Because battery is aging, it is becoming less efficient. So the RTE difference starts to go. And because of that, you will take a hit. You have to pay for the LDs, and that will impact your net revenue on the project and impact your cash flow. Then you take that all this information and you put it all together into one graph, right? So this is the overall cash flow graph that you get. So on the
Hey, Jakir, got a question from Pedro, or Pedro's hand is up. Go ahead, Pedro.
Yeah, sorry. Could you go back to the LDs just to understand, is this a probabilistic scenario where errors can occur on the losses, or is based on, let's say, undersized scenarios?
Yeah. So that is based on the comparison of the RTE the project is experiencing and what we have in the contract, the guaranteed RTE, which is 88%, right? So the project, what it is giving us is an RTE around 85%. And the way we get this RTE of 85%, there are several factors that goes into it. So the location of the project, that impacts how much auxiliary consumption is going to happen, and that plays a role in the RTE. Also, the selection of the equipment, because some equipments are more efficient than others. So in this case, the battery, inverter, and the enclosure models that we use is playing a big role in the amount of the RTE that you are observing there. So to your point about probabilistic or deterministic, the results that you get are deterministic based on the models that you have used and the location of your site. And then these models, when you create that, we create these models and validate this model based on exact data on how this equipment performs. So I would say it's more deterministic and less probabilistic.
And also,
so in this case, the difference is the 88 versus the 85%.
Correct, yes. At year 0, it's 88 minus 85. And then with time, the battery RTE goes down from 85 to all the way, I think, 83 or so. So you can see that if you go to the GNCSP.
And it's there in the table in the report, Jakir, as well, and the degradation portion.
Oh, yeah, this should be there as well.
The DC-DC RTE.
Yeah, so the DC-DC RTE is here. So you can see the battery DC-DC RTE is going down from 95 initially to 93. And I also wanted to show the POI. And you can also get the POI RTE. You can get that here, and you'll see that going down as well. So, yeah. Does that answer your question, Pedro?
Yes, thank you.
All right, we were reviewing our cash flow image here, results. Yeah, on the large red bar here on the negative side is your CapEx initially. Then you have your ITC, we're applying it at year 0, that's that blue bar. And the orange bar here is your depreciation. So you will see that up until year 5, you have your depreciation. Then you have your net revenue, operating revenue in green, and then your OPEX is showing up on the negative axis in this yellow. So everything is packed up together, and the unlevered IRR that you accrue in this case is around 9.5%. And if you were to assume a discount rate of 5%, the project was going to break even at around year 13. Okay. So now that we have seen how to go about designing it and optimizing a design for one particular configuration, now we can go back to the slide and look at some iteration of it. So all this we have done for AC augmentation. Now, if we want to understand, okay, instead of doing AC augmentation, if we were going to do DC augmentation, how my results vary, right? So you can actually do that as well. And we also provided an example file that's called same file name, but underscore DC. You can go ahead and run that. But in that scenario, you will select the DC option under augmentation type, run the augmentation optimizer. Is going to give you an augmentation schedule based on DC. And once you look at the results, you will see that augmentation schedule is a little bit different for AC versus DC. Not a lot, but there are some difference based on the parameters that we have selected. So once we've done the augmentation AC and DC, we have some observations. So first observation that I wanted to highlight is you will see that there is degradation difference between AC and DC, even though it shows minimal for this case, but there actually are, and then for different scenarios it can get bigger. But the more important thing to notice is compare this green and blue curves with this orange curve. And this orange curve is what we had of the initial systems degradation, right? And that's what is a typical practice here. You make an initial system SOH degradation, and you assume that's going to be the degradation even after augmentation. And that's actually not the case. You will see that as you are adding more battery capacity, so you'll see up until year 3, those all are same. But as you kept adding more new batteries through augmentation, the degradation of your initial system started to slow down. And that's an important factor to take into account. You'll see that over the period of 20 years, it can be as large as, in this case, I think 6% or so. So that's very important nuance that often gets missed if we apply the same degradation curve for all augmentation phases. Second thing, we went over it as a result of the augmentation optimizer, so I'm not going to cover it any further here. The one that I want to cover is the comparison of the augmentation schedule, so AC versus DC. So in this case, both shows that both are having a first 3-year overbuild, but then the overbuild amount is different. So DC had more overbuild done at year 3, more augmentation done at year 3 than the AC. AC augmentations are happening at year 3, year 7, and year 12. And then DC augmentations are happening at year 3, year 8, and year 14. So we kept everything same, location same, use case same, equipment same, just varied the type of augmentation. And that is causing us the augmentation schedule to be different. We also covered this observation that round trip efficiency, like we were discussing, our target is 88, and then our actual RTE was much less than that, and that cost us RTELD that we could see. Overall cost of ownership comparison, so we observed that the AC system was more expensive than the DC one. In this case, it was more driven by the cost of inverters, and around 1.2% difference in the cost overall NPV cost of the project between AC augmentation and DC augmentation. And then when you put it together, if you give the same revenue and cost assumptions on the IRR, DC one gives you 9.7% IRR versus the AC one, which we just ran around 9.5. So there is a gain of 0.2% switching from AC augmentation to DC augmentation. And also wanted to show you, of course, different market has different revenue streams depending on your contract structure. Your return is also going to be very impactful. That's very intuitive. But if you tie that for this example, tolling agreement, we got 9.5% for AC. For the merchant market, the revenues for ERCOT market is not doing that great. With the current market rates, doesn't look like it's going to be profitable on just based going by the merchant market. If you tag along some other contract strategy or other revenue stacks on top of it, then maybe you can make it work, but just going by merchant market makes it difficult to pencil out. And then So that brings us to the end of, okay, the parameter that can potentially impact, how impactful deployment strategies are, how impactful different contract types are to my return. Now, if you want to take this thought and expand it over markets, right? So let's say now I want to develop this same 100 megawatt, 400 megawatt hour battery and think of it from a developer portfolio perspective. You have the option to deploy that capital either in ERCOT or PJM or MISO, which is the best market for you to deploy that capital. So in this case, we try to design the same battery, 100 megawatt, 400 megawatt hour for the 6 different markets. And what we got is the overall NPV cost. It came out to be the cheapest for ERCOT because ERCOT 1, the dispatch profile was not utilizing the battery as much compared to SPP. Looked like you every day you are doing energy arbitrage and a full cycle and using the battery a lot. So that eventually caused SPP and NI ISO, New York ISO, their cost to be on the higher side than ERCOT and others. So over the spectrum here, we end up getting around like 10% difference in cost. So then the next question obviously becomes, how does that impact our IRR? And how does we gain efficiency compared to the current practice? Because right now, everywhere you're going, you're just trying to buy a 1 cycle per day battery, right? You're not really taking the use case of the market into account when you're trying to purchase that battery. So what in this next graph here is, we have 2 approaches. One is that use case specific sizing, like what we just saw in our exercise today, where we are inputting a market specific signal, versus a generic sizing where you don't know, you're not actually inputting a market specific signal, rather just saying, I'm going to do a 1 cycle per day battery. So that's one. Generic sizing is the blue one, and then the use case specific sizing is the green one. And what you end up seeing there in almost all the markets, the generic sizing actually is giving you less IRR because most of those markets, the battery are not actually doing 1 cycle a day. So you are actually buying a battery that you don't really need. You're expending more, and in that process, your cost is elevated, and then that's causing you to get less IRR. And compared to that, if you shift to use case specific sizing, you can get better cost assumption and performance assumptions or performance matrices that allows you to optimize your IRR. And in this case, for ERCOT, we could even see as much as 2% difference in IRR, especially in a market that is that competitive and where the revenue prices are going down. 2% is huge. So there is a lot of efficiency that can be gained by doing use case specific sizing.
And just a quick heads up, what you see here is IRR. It's not net present value cost. The y-axis there, that's a typo, so feel free to ignore that. So I just wanted to clarify that for folks.
Yeah, thanks for catching that, Sherif. I missed it. Yep.
Sure. All right, I think we have Muhammad has his hands up. Go ahead, Muhammad.
Yeah, thanks. Jakir, if you don't mind going back to the augmentation tab question.
Yeah.
When you choose there's an option to choose an augmentation schedule, right? The second one that's grayed out.
Yes.
So if I choose that, what is it? What file I need to input there? Like the way I want to see the
Yeah. So let me clarify something. So for augmentation schedule type, you have 2 options, either user input or augmentation optimizer. If you go with the augmentation optimizer is our default option. So if you go with that, then you don't need to input anything. You run the augmentation optimizer, it's going to produce that augmentation schedule, and it's going to populate it here.
For that specific OEM that I'm going to choose, for instance.
Yeah, but for example, you have an OEM and they gave you an augmentation schedule and you want to input that, then you can select the user input option. And if you select the user input option, then you see that this is an input, right? So then you have to input that file. And where you input that file is you will go into the Storlytics user files folder, go to input profiles, augmentation schedules, right? So this is where you will need to put that file. And if I open a file, you will see there are three things this file is asking for. First thing is the number of years. And then the second thing is that how much capacity, energy capacity in kWh you are planning to add. And the third column is how much inverter capacity in kW you are planning to add. So you input those and then you save this file, and then you will be able to select that from the drop-down option here.
Okay, that's great. So if I have a proposal from X OEM and I have the augmentation schedule from them, I can use one of these schedules, Excel files,
Correct.
to save it as to suit what I have so that I can simulate something similar to what I got from the OEM.
Exactly.
That will allow you to verify what the OEMs are giving.
Exactly.
Will
That's what I'm
will
after.
that-
Exactly.
Exactly. Yep.
Okay. Thanks a lot. That's really a great feature. Thank you, Jakir.
Any other question do you have on the chat?
Let me check here. There was a question about, is there any limitation on the duration of the system that can be ran within Storlytics?
No. Yeah, we don't have any limitation. You can do any kind of system, any type of system and size of system. And as you can go as small as a residential systems as well.
And then in the battery, so one thing, for example, you just have to be mindful of, some batteries have C rate limits, right, which is the inverse of duration, right? So you just have to make sure that your system duration is not causing the C rate to be exceeded or anything like that.
Yeah.
Okay. All right, I see two hands up here. I think Muhammad was first. Go ahead, Muhammad. What was the question?
Yeah, and the same token, we spoke about the augmentation under the system specs tab. If I have a certain proposal from an OEM with a certain number of modules per rack and racks, a certain architecture, number of inverters per, or number of racks per inverter, I can change that here, right? And then redo the simulation.
Absolutely.
You can easily do that.
Me.
And then if you want to do, let's say, an integrated product, you can do that as well. So let's say SunGlow, right? You can select it, come here and just input number of SunGlow blocks. These are going to be automatically updated.
Oh, excellent. Okay, thanks.
Pedro, go ahead.
Just to make sure if I understand the difference between what you call use case specific sizing and generic, can you explain? So what is case specific sizing has to do with the market itself, or?
Yeah. So I'll give a real quick explanation, and Jakir, you can fill in the gaps if I miss anything. So in general, use case specific sizing refers to when you're actually designing the battery system based on how it's actually going to be dispatched, its exact location, and really all the features that relate to that project. For example, how the auxiliary load is sourced, whether it's from the POI or it's from a separate source. And generic sizing just refers to when you're just going off of what the OEM is saying or just very generic assumptions. So a lot of people, when they're designing BESS projects, they just make an assumption that, oh yeah, it's just going to be one cycle per day. We're assuming the temperature is always going to be 25 degrees Celsius, standard temperature, pressure conditions, and everything. So that's the main differentiation. And Jakir, go ahead. You can fill in the gap.
I think you covered it pretty well. Just you make very high level assumption. Yeah, my auxiliaries are 2%, right? And then my system losses are 5%. RT is 88%. You make that kind of high level assumptions and then basically go about the sizing. So that's what we call generic. And then use case is like Sherif was saying, because we know like these things are not constant, depending on temperature and current that's flowing through the wires, these losses are varying, the performance are changing. So that's what we call it use case specific, because so that's more detailed and more granular than the generic assumptions.
Maybe just another. So the use case is also based on a dispatch strategy. is this dispatch strategy already in the program according to different markets, or is something that we also need to add?
Yeah. So we do provide it in the program for the North America market. So you have this feature generate from market signals. So you can come here and you will see that all the different markets in North America are listed here. So that option is there. For market outside the North America, you can bring in your own profile and just load it to import it the software through the CSV file option, because this is CSV. So nothing prevents you to import any use case profile that you want to import.
Okay, understood.
Perfect.
All right. Go ahead, Jakir.
No, I said perfect. Let's see if we have any other question.
I don't see any other questions in the chat.
I see one hands raised. Go ahead, Madhu.
Hey, do we have this recording available?
Yes, it will be
Yes,
made available after the call.
Okay, that's appreciated.
Yeah, Mohammed.
Sorry, one last question. The market signals that you refer to that are available for North America, are these for multiple revenue streams?
Right
Or
now,
depending on the market?
yeah, it depends on the market. It's a co-optimization. So we are partner with ES Energy, and they are the one who's providing this dispatch signal. So depending on the market and the available ancillary services, they do an energy and ancillary service co-optimization and provide these signals.
In one file?
Yeah, in one file.
Okay, thanks a lot.
Great question.
All right, see, we have another question here. Are you seeing the market shift from 314 amp hour LFP cells to 500 amp hour plus formats? If so, how large are the real world degradation differences under typical utility scale duty cycles? And what are the main drivers behind them? C rate, thermal profile, depth of discharge, chemistry, or platform?
Yeah, that's a loaded one. I'll take a stab. Yes, we definitely, I would say still most of the projects that have been placed in service are being around 314. We are seeing project proposals being put forward by the OEMs are including 500 plus ampere hours, more and more. One of the issue is that with these higher ampere hour cells, there is very limited runtime and testing data available on this. So we're still early stage, but what our observation is the degradation performance are better than the old smaller ampere hour cells. You also see better RTE efficiency in the DC-DC RTE of the cells as you go to higher hours. And let's see the next part of the question. Yeah, so mostly what I have seen is that degradation performance are better, loss performance are better, and also the form factors are better, helping them with getting more energy dense, and the container sizes are growing larger and larger. And also, I think we're shifting a more shift towards AC blocks options. So more and more integrators are trying to put inverters and batteries inside a single block. So yeah, that's the observation. Mine.
And just to clarify, when Jakir is saying the container sizes are getting larger and larger, that's referring to the amount of energy that can be withheld within them, right? Jakir, are you talking about increased energy density or reduced energy density?
I'm talking about increased energy density. Right.
Yep. Okay. Yeah, and we're also in this version, you can see the BESS model builder down there. So this model builder is going to simplify the process of creating battery, inverter, and enclosure models. We're also making that model builder free for battery OEMs. So any battery OEM can download the model builder on its own and create a model and basically send it to you as the user or as the prospect of the battery OEM to simulate your own project. And again, it's free for the OEMs integrators, so they can get quick access and put in the parameters that represent their models, their products, basically. All right, another question here from Muhammad Shahab. Jakir, I think we have a 6.25 megawatt hour block model coming up, right?
Yeah, I think right now we don't have one. I think the highest we have is a 5.015, but yeah, we're working on a 6.25. We'll add them.
Okay, 2 minutes left here. Of course, we wanted to do the third use case, which is the solar plus storage, but fortunately time did not permit us here. So are there any other questions? Seeing any hands up? In that case, we appreciate everyone attending, and as a thank you, if there's interest from anyone, feel free to reach out to accounts@storlytics.net to receive your attendance promo code, which will give you a discount for Click software. Definitely don't hesitate to reach out to get that promo code. Again, thank you for attending, and we'll catch you next time. Thank you, everyone.